Hey everyone, welcome back. Tonight we're talking about something that might change how you see humanity's place in the universe. We're diving into a cosmic truth that's both beautiful and terrifying, a reality that science fiction conveniently ignores, a prison made not of walls but of physics itself. We're going to explore why, despite all our dreams of exploring distant galaxies, meeting alien civilizations on the other side of the universe, or colonizing worlds beyond our galactic home, we are almost certainly trapped. Forever. Confined to the Milky Way galaxy. And even that might be generous. So settle in, get comfortable, maybe dim the lights, because tonight we're going to journey to the edges of what's possible and discover the invisible walls that surround our entire civilization, the barriers that no amount of ingenuity, no miracle of engineering and no leap of technology can overcome. We're talking about the fundamental laws of physics, the structure of space-time itself, and the accelerating expansion of a universe that's slowly, inexorably, making the dream of intergalactic travel not just difficult, but physically impossible. Before we begin, if you enjoy journeys like this, slow, atmospheric, and full of the strange truths hiding in our universe, make sure to subscribe. It helps the channel keep exploring these mysteries with you. Now, let the story begin. This isn't a story about giving up. It's a story about understanding reality, about confronting the actual scale of the cosmos, about appreciating just how precious and isolated our little island of stars truly is. So let's begin at the beginning. Let's talk about the prison we call home. Look up at the night sky on a clear moonless evening far from city lights. That faint milky band stretching across the darkness is our galaxy, the Milky Way seen from inside. We're embedded in it, floating in one of its spiral arms, about 26,000 light years from its bright central bulge. Everything you can see with your naked eye, every single star twinkling in the darkness, every constellation that ancient humans named and built myths around, all of it, every point of light belongs to our galaxy. They're our neighbours in this vast stellar city. But here's the thing that most people don't truly grasp. The Milky Way isn't just big. It's incomprehensibly, devastatingly, mind-shatteringly enormous. And yet, in the grand scheme of the universe, it's just one galaxy among hundreds of billions. A speck, a mote of dust in a cosmic ocean so vast that the human mind simply cannot process it. We've gotten good at throwing around big numbers. We talk casually about light years as if they're comprehensible units of measurement. We've seen enough science documentaries and read enough articles that we think we understand cosmic distances, but we don't. We really, truly don't. Because our brains evolved to understand the distance between the cave and the river, between one tree and another, between our village and the neighbouring tribe. We did not evolve to comprehend distances measured in trillions of miles, distances so vast that light itself, the fastest thing in the universe, takes hundreds of thousands of years to cross them. And this is where our cosmic prison reveals itself. Because when we talk about escaping the Milky Way, we're not talking about a difficult engineering challenge. We're not talking about something that requires better technology, more funding, or a few more centuries of scientific progress. We're talking about something that runs headlong into the most fundamental laws of nature. Laws that cannot be bent, cannot be broken, and cannot be circumvented by any amount of cleverness or determination. The speed of light is absolute. It's not just fast, it's the cosmic speed limit. Nothing with mass can reach it. Nothing with mass can exceed it. Not now, not ever, not with any conceivable technology. This isn't a limitation of our current understanding. This is baked into the fabric of reality itself, into the structure of space-time. And when you combine this absolute speed limit with the staggering distances involved in intergalactic travel, you begin to see the problem. But it gets worse, much worse. Because the universe isn't static, it's expanding, not expanding into something, but expanding in itself. Space itself is stretching, like the surface of an inflating balloon, and this expansion is accelerating, driven by a mysterious force we call dark energy. Every second, galaxies beyond our local neighbourhood are receding from us faster and faster, and at some point they're receding faster than light itself can travel, not because they're moving through space faster than light, which would be impossible, but because space itself is expanding between us and them. This means that right now, at this very moment, there are galaxies we can see in our telescopes that we could never reach, even if we could somehow travel at the speed of light. The space between us and them is expanding faster than we could ever cross it. We could point our hypothetical light-speed starship at them and accelerate forever, and we'd never get any closer. They're gone, unreachable, lost beyond an invisible horizon called the cosmological event horizon. And that horizon is getting closer. Every moment that passes, more and more galaxies slip beyond it. More and more of the universe becomes forever inaccessible. We're living in a shrinking bubble of reachability, surrounded by an ever-growing ocean of impossible distance. Now, you might be thinking, okay, but we're not talking about reaching those distant galaxies. We're talking about escaping our own galaxy. Reaching our nearest neighbour, Andromeda perhaps, or exploring the other members of our local galactic neighbourhood. Surely that's possible, right? Surely that's within the realm of achievable goals. And here's where we need to be honest. Here's where we need to look at the actual numbers, the actual physics, the actual energy requirements. Because when you really sit down and calculate what it would take to send even a small spacecraft to another galaxy, the answer is sobering. The answer is crushing. The answer is no. Not with any technology we can currently envision. Not with any fuel source we know of. Not even with perfect matter-antimatter conversion, which releases more energy per unit mass than anything else in physics. The distances are too vast. The speeds required are too high. The energy costs are too astronomical. And the timescales are too long. Even if we could solve the technical problems, even if we could build a ship capable of reaching a significant fraction of light speed, the journey would take millions of years. Millions of years. Longer than our species has existed. Longer than most species exist before going extinct. Longer than civilizations last. Longer than we can plan for or prepare for or even imagine maintaining continuity across. So we're going to walk through this together. We're going to look at each barrier, each impossibility, each fundamental limit that stands between us and the stars beyond our galaxy. We're going to understand the scale of the Milky Way itself. We're going to explore why the speed of light is an absolute barrier. We're going to calculate the energy requirements for interstellar and intergalactic travel. We're going to understand time dilation and what it means for any hypothetical travellers. We're going to learn about the expanding universe and why it makes the problem exponentially worse. And we're going to confront the sobering reality that we are, in all likelihood, permanently confined to this one galaxy. But here's the beautiful part. Here's the silver lining. The Milky Way is vast. It contains somewhere between 200 billion and 400 billion stars. Billions upon billions of worlds. More stars than humans have ever lived. More potential homes than our species could ever explore. If we can solve the comparatively easier problem of interstellar travel within our own galaxy, if we can find a way to spread beyond our solar system to neighbouring stars, we have an entire galaxy to explore. A realm so vast that it might as well be infinite from our perspective. The cage is big, the prison is spacious beyond imagination, but it is, nonetheless, a cage. And tonight, we're going to understand exactly why. Let's start by really, truly understanding the scale of our galactic home. Because until you grasp just how monumentally large the Milky Way is, you can't fully appreciate why escaping it is such an impossibility. The Milky Way is a barred spiral galaxy. Picture a flat disk with a bright bulge in the centre and graceful spiral arms curving outward, filled with hundreds of billions of stars, nebulae, star clusters, and planets. At its widest point, the galactic disk measures approximately 100,000 light-years across. Let that sink in for a moment. 100,000 light years. Now, a light year is the distance that light travels in 1 year, moving at its constant speed of about 186,000 miles per second, or roughly 300,000 kilometers per second. In 1 year, light crosses about 5.88 trillion miles. That's nearly 6 trillion miles, and our galaxy is 100,000 of these light years across. Do the math, and the Milky Way's diameter is roughly 588,000 trillion miles, or in more manageable notation, about 5.88 followed by 17 zeros, miles, across. And that's just the visible disk, the part we can easily see and measure. The galaxy also has a halo, a roughly spherical region extending outward, populated by ancient globular clusters and dark matter. This halo might extend the galaxy's influence to perhaps 200,000 light-years or more in certain directions. To put this in perspective, the distance from Earth to the Sun is about 93 million miles. We call this distance 1 astronomical unit, or 1 AU. It takes light from the Sun about 8 minutes to reach Earth. 8 minutes. The distance across our entire solar system, if we measure out to Neptune's orbit, is about 30 AU. Maybe 60 AU if we're generous, and include the Kuiper belt. Light takes about 8 hours to reach Neptune. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That's over 4 years for light to make the journey. In terms of our familiar AU, that's roughly 268,000 AU. If you were to travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reaches speeds of about 430,000 miles per hour, near its closest approach to the Sun, it would take you over 6,000 years to reach Proxima Centauri. 6,000 years for our nearest stellar neighbour. But Proxima Centauri is in our local neighbourhood. It's practically next door in galactic terms, the centre of the Milky Way, where a supermassive black hole lurks surrounded by a dense cluster of ancient stars, lies about 26,000 light-years from Earth. We're in the Orion Arm, a minor spiral arm about 2/3 of the way out from the centre. We're in the galactic suburbs, you might say. If you wanted to travel from one edge of the Milky Way to the other, passing through the centre, you'd need to cover that full 100,000 light-year distance. At light speed, this journey takes 100,000 years. At the speed of Voyager 1, which is currently humanity's most distant spacecraft, travelling at about 38,000 miles per hour relative to the Sun, that same journey would take about 1.7 billion years. Billion, with a B. Let's try to make this more concrete. Imagine you could shrink the Milky Way down so that the distance from Earth to the Sun, those 93 million miles, was just 1 inch. On this scale, the distance to Proxima Centauri would be about 4.24 inches. Our solar system's entire extent out to Neptune would be about 1 inch. And the Milky Way? On this scale, where the Earth-Sun distance is 1 inch, the diameter of the galaxy would be about 100,000 inches, which is about 1.58 miles. So if Earth is sitting here and the Sun is 1 inch away, the nearest star is about 4 inches away, and the galaxy stretches for over 1.5 miles in diameter. That's the scale we're dealing with. And remember, this is just our galaxy. This is home. This is the neighbourhood we're trying to escape from. The Milky Way isn't uniformly populated with stars, of course. The central bulge, that bright core region about 10,000 light-years across, contains a dense collection of mostly old red stars. This is where things get crowded. In this region, stars can be separated by as little as 1/10 of a light-year, compared to the roughly 4 light-years between stars in our solar neighbourhood. If Earth were located in the galactic core instead of out here in the spiral arms, our night sky would be utterly transformed. Instead of seeing a few thousand stars with the naked eye, we'd see hundreds of thousands, perhaps millions. The night sky would never be truly dark. There would be no Milky Way band to see, because we'd be immersed in its brightest region. The spiral arms, where most of the star formation happens, contain younger, hotter blue stars, giant molecular clouds of gas and dust, and brilliant stellar nurseries where new stars are being born. Our Sun orbits the galactic centre at a stately pace of about 515,000 miles per hour. At this speed, it takes roughly 230 million years to complete one orbit. One galactic year. The last time our solar system was in this position, dinosaurs were just starting to appear on Earth. Since Earth formed about 4.5 billion years ago, our planet has made roughly 20 trips around the galaxy. But here's something fascinating and sobering. Despite the enormous number of stars in the galaxy, somewhere between 2 and 400 billion, space is so vast that the average distance between stars is still measured in light years. Most of the galaxy is empty space. If you were standing on a planet orbiting a star in the middle of the Milky Way and looked around, space would still appear largely empty. You'd see more stars than we do, certainly, but you wouldn't be bumping into them. The distances are just too vast. This brings us to an important point. When we talk about escaping the Milky Way, we're not just talking about leaving behind the 100 billion or so stars in the galactic disk. We're also talking about escaping the gravitational influence of the galaxy itself. Because the Milky Way isn't just a collection of stars moving independently through space. It's a gravitationally bound system. All these stars, all this gas and dust, all the dark matter that makes up most of the galaxy's mass, they're all held together by gravity. They orbit around a common centre of mass. The total mass of the Milky Way, including the dark matter that we can't see but can detect through its gravitational effects, is estimated to be somewhere around 1.5 trillion times the mass of our Sun. That's 1.5 trillion solar masses, and all of that mass creates a gravitational well. To truly escape the galaxy, you'd need to achieve the galactic escape velocity from your starting position. From our location in the Orion Arm, that escape velocity is approximately 550 kilometers per second, or about 1.2 million miles per hour. Now that might not sound impossible. After all, we've achieved Earth's escape velocity of about 25,000 miles per hour. We've sent spacecraft to the outer solar system and beyond. Surely another factor of 50 isn't insurmountable. But here's the problem. Achieving Earth's escape velocity requires fighting against the gravitational pull of one planet. Achieving solar escape velocity, about 138,000 miles per hour from Earth's orbit, requires fighting the Sun's much stronger gravity. But these are local gravitational fields. Once you escape them, you're essentially free. You can coast. But galactic escape is different. The galaxy's gravitational influence extends far beyond the visible disk. The dark matter halo reaches out hundreds of thousands of light years. You'd need to not only reach that escape velocity, but maintain enough momentum to carry you across distances so vast that the journey would take tens of thousands of years, even if you were travelling at a significant fraction of light speed. And remember, we're not actually trying to just escape the galaxy's gravity. We're trying to reach another galaxy. The nearest major galaxy to us, Andromeda, is about 2.5 million light-years away. Even if you could somehow travel at the speed of light, which you can't, the journey would take 2.5 million years. At more realistic speeds, say 1% of light speed, which would still require technology far beyond anything we can currently imagine, the journey would take 250 million years. That's longer than the age of all dinosaurs. That's longer than complex life has existed on land. The scale is incomprehensible. The distances are so vast that our brains literally cannot process them in any meaningful way. We can calculate them. We can write down the numbers, but we can't truly understand them in the visceral way we understand the distance to the store, or across town, or even across the country. And this is just the first barrier. This is just understanding the playing field. Because the next question is, okay, so it's far. Really far. But can't we just go really fast? Can't we build ships that approach the speed of light, put humans or robots in suspended animation or digital storage, and send them out into the cosmic deep to make the journey? And that's when we encounter the second barrier. The absolute, unbreakable, fundamental law of nature that makes this dream impossible. we encounter the speed of light itself and the iron law that nothing with mass can ever reach it. There's something profoundly unfair about the speed of light. It tantalizes us with possibility while simultaneously crushing our dreams against the hard rock of reality. It's the fastest speed possible, the cosmic speed limit, and yet it's not nearly fast enough for the journeys we want to take. Light travels at 297,458 meters per second in a vacuum. We usually round this to 300,000 kilometers per second, or about 186,000 miles per second. This is blazingly, incomprehensibly fast by everyday standards. In 1 second, light can circle the Earth's equator about 7.5 times. In 1 second, a beam of light travels roughly the distance from Earth to the Moon and 1/3 of the way back. Every year it covers those 5.88 trillion miles we call a light year, and this speed isn't just the speed at which light happens to travel, it's fundamental. It's baked into the structure of the universe itself. The speed of light, usually denoted by the letter c, appears in equations all across physics. It relates mass to energy in Einstein's famous E-KMC2. It defines the rate at which cause and effect can propagate through space. It determines the structure of space-time itself. When Einstein developed his theory of special relativity in 1905, he made a radical proposal. He suggested that the speed of light is the same for all observers, regardless of their motion or the motion of the light source. This seems bizarre at first. After all, if you're on a train moving forward at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing beside the tracks would see the ball moving at 70 miles per hour, right? The speeds add up. But Einstein said, that's not how light works. If you're on a spaceship moving forward at half the speed of light and you shine a flashlight forward, you don't see that light moving away from you at 1.5 times the speed of light. You see it moving at exactly the speed of light. And remarkably, someone standing still watching you would also see that light moving at exactly the speed of light, not the 1.5 times the speed of light you might expect, from adding the speeds together. This is so counterintuitive that it breaks our everyday understanding of how motion works. But it's not just a theory. It's been tested thousands upon thousands of times. It's the foundation of GPS satellites, particle accelerators, and countless other technologies. It's as solid a fact as anything in science, and from this simple, strange fact flows a cascade of consequences that reshape our understanding of reality. Time and space are not absolute. They're relative, depending on the observer's motion. Moving clocks tick more slowly. Moving rulers shrink in the direction of motion. And crucially, vitally, devastatingly for our dreams of cosmic exploration, nothing with mass can ever reach the speed of light. Here's why. As you accelerate an object, you increase its kinetic energy. In everyday life, at everyday speeds, this energy increases in a simple, straightforward way. Double the velocity, quadruple the energy. But as you approach the speed of light, something strange happens. The relationship changes. The energy required to accelerate the object increases not linearly, but exponentially, approaching infinity as you approach light speed. This isn't because the object is getting heavier, despite what you might have read in older textbooks. The object's rest mass, its intrinsic mass, doesn't change. What changes is its inertia, its resistance to further acceleration. The faster you're already going, the harder it becomes to go even faster. And as you approach the speed of light, it becomes infinitely hard. To actually reach the speed of light would require infinite energy. Infinite energy. This means that no matter how advanced your technology, no matter how much fuel you have, no matter how powerful your engines, you cannot accelerate a spacecraft with mass to the speed of light. You can get close. You can reach 99% of light speed, or 99.9%, or 99.99%. But you can never reach 100%. The energy requirements grow without bound. Let's put some numbers to this. Imagine you have a small spacecraft, say 1,000 kilograms, including fuel, payload, and structure. That's about the mass of a compact car. Now let's say you want to accelerate this spacecraft to just 10% of the speed of light, or 0.1 c. That's about 30,000 kilometers per second, or roughly 67 million miles per hour. That's fast enough to cross the distance from Earth to the Moon in about 13 seconds. How much energy would you need? Using the relativistic kinetic energy formula, we find that you'd need about 4.5 times 10 to the 18th joules. That's 4.5 followed by 18 zeros. To put that in perspective, the total energy consumption of all of human civilization in an entire year is roughly 5.8 times 10 to the 20th joules. So accelerating this 1-ton spacecraft to 10% light speed would require almost 1% of humanity's annual energy budget. For one small craft. Just to get it up to speed, not accounting for deceleration or any of the other energy needs for a journey. Now let's say you want to go faster. Let's aim for 90% of light speed, or 0.1 c. Now the energy required jumps to about 1.2 times 10 to the 20th joules. That's over 20% of humanity's total annual energy consumption, just to accelerate this one small spacecraft. And we haven't even talked about where this energy comes from, how you generate it, how you store it, or how you convert it into thrust. At 99% of light speed, the energy requirement is about 6.3 times 10 to the 20th joules, more than humanity's entire annual energy budget, for one small spacecraft. And at 99.9% of a light speed, we're looking at nearly 2 trillion joules of energy, roughly 3 times humanity's annual energy consumption, just to accelerate 1 ton of matter. You see the problem. The energy requirements don't just increase linearly with speed, they increase exponentially, approaching infinity as you approach light speed. This is a fundamental barrier. It's not an engineering challenge, it's a law of nature. But wait, you might say, what about photons? Light itself moves at the speed of light, so clearly it's possible to move that fast. How do photons do it? The answer is simple and profound. Photons have no mass. Zero. They're pure energy, pure electromagnetic radiation. And in relativity, anything with zero mass must travel at exactly the speed of light. It has no choice. Photons can't be accelerated or decelerated. They don't experience time or distance in the way we do. From a photon's perspective, if such a thing could be said to exist, it's emitted and absorbed in the same instant, regardless of how far it travels from our perspective. This is the fundamental divide. Massless particles like photons travel at light speed. Particles with mass cannot. And since spaceships, humans, robots, and all the things we might want to send to other galaxies have mass, they're stuck below light speed. Always. Now there's another aspect of this we need to discuss because it's often misunderstood. As you approach the speed of light, time dilation occurs. Moving clocks tick more slowly compared to stationary ones. This is a real physical effect, not an illusion. If you could somehow build a spaceship capable of travelling at 99.9% of light speed, and you took a journey to a star 100 light years away, from Earth's perspective the journey would take about 100 years. But from your perspective, aboard the ship time would be dilated by a factor of about 22.4. The journey would feel like only about 4.5 years. This is often presented as a solution to the time problem. See, people say, from the traveller's perspective, the journey is much shorter. Time dilation makes it feasible. But this is cold comfort for several reasons. First, the energy requirements to reach these relativistic speeds are still astronomical and probably insurmountable, as we've discussed. Second, even if you could build such a ship, from Earth's perspective the journey still takes 100 years. If you're sending messages back and forth, each exchange takes centuries. If you're trying to maintain any kind of civilization or continuity, this becomes impossible. Entire generations would live and die waiting for news from the travellers. Third, and perhaps most chillingly, the travellers would be stepping out of sync with the rest of humanity. When they returned from their journey, everyone they knew would be long dead. Their entire civilization might have risen and fallen. They'd be temporal refugees, adrift in time, separated from everything they knew by an unbridgeable gulf of years. And fourth, this time dilation only helps with journeys within the galaxy, or perhaps to very nearby galaxies if you could reach high enough speeds. For truly intergalactic journeys, to galaxies millions or tens of millions of light years away, even time dilation can't compress the subjective journey time to something a human crew could survive. At 99.9% light speed, a journey to Andromeda would still take about 56,000 years from the traveller's perspective. That's longer than human civilization has existed. So the speed of light limit isn't just an inconvenience, it's a fundamental barrier that cannot be overcome. It means that the travel times for intergalactic journeys are measured in millions of years, even in the best case scenarios. It means the energy requirements are so vast as to be functionally impossible. And it means that even if we could somehow solve these problems, the time dilation effects would rip travellers out of any meaningful connection with the civilization that sent them. But surely you might be thinking there must be a loophole. What about wormholes? What about warp drives? What about quantum entanglement or exotic matter? Or the dozens of other science fiction solutions we've come up with? We'll get to those. But first, let's look at what we can actually do right now. Let's examine the fastest machines humanity has ever built and see just how pathetically slow they are compared to what we'd need for intergalactic travel. Let's talk about what we can actually do with our current technology. Because before we get lost in hypotheticals about fusion drives and antimatter engines, and other exotic propulsion systems that might exist someday, we need to understand where we are right now. We need to appreciate just how vast the gap is between what we can do and what we'd need to do to reach even the nearest stars, let alone the nearest galaxies. The fastest spacecraft humanity has ever built is NASA's Parker Solar Probe. Launched in August 2018, this remarkable machine was designed to study the Sun's outer atmosphere, the corona, and the origins of the solar wind. To do this, it needed to get close. Really close. Closer than any spacecraft has ever ventured. In December 2024, the Parker Solar Probe made its closest approach to the Sun, coming within about 3.8 million miles of the solar surface. For perspective, that's about 16 times closer than Mercury's orbit. At this distance, the spacecraft endured temperatures of roughly 2,500 degrees Fahrenheit, protected only by a 4.5-inch thick carbon composite heat shield. But what's really remarkable is the speed. As the Parker Solar Probe swings around the Sun at perihelion, its closest approach, it reaches speeds of approximately 430,000 miles per hour, or about 700,000 kilometers per hour. That's roughly 191 kilometers per second. It's the fastest human-made object ever built, and it's not particularly close. Let's put that speed in context. At 430,000 miles per hour, the Parker Solar Probe is moving at about 0.064% of the speed of light. That's 0.06%, not 6%, 0.06. If the speed of light is 100, the Parker Solar Probe is moving at 0.064. At this speed, which again is the fastest we've ever achieved, the Parker Solar Probe could travel from New York to Los Angeles in about 20 seconds. It could circle the Earth's equator in about 3.5 minutes. It's legitimately fast by any everyday standard. But let's see what happens when we scale up to stellar and galactic distances. At this speed, how long would it take to reach Proxima Centauri, our nearest stellar neighbour at 424 light-years away? The answer is about 6,300 years, 6,300 years. That's longer than human civilization has existed, longer than recorded history. It's the distance in time from now back to the first stone monuments, the first cities, the very dawn of agriculture. And Proxima Centauri is right next door. It's in our local stellar neighbourhood. What about crossing the galaxy? At 430,000 miles per hour, crossing the Milky Way's 100,000 light-year diameter would take about 171 million years. That's the timescale we're talking about. Not centuries, not millennia, hundreds of millions of years. And Andromeda, the nearest major galaxy at 2.5 million light-years. At Parker Solar Probe speed, the journey would take about 4.3 billion years. That's roughly the age of the Earth. It's close to the age of the Sun. It's a timescale so vast that it's effectively eternal from any human perspective. Now you might say, okay, but the Parker Solar Probe wasn't designed for interstellar travel. It achieved those speeds by falling toward the Sun, using its gravity to accelerate. Surely if we designed a spacecraft specifically for deep space exploration, we could do better. Let's look at some other notable spacecraft. The Voyager probes, launched in 1977, are currently the most distant human-made objects from Earth. Voyager 1 is travelling at about 38,000 miles per hour relative to the Sun, or about 17 kilometers per second. At this speed, it would take roughly 75,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. Crossing the galaxy would take about 1.9 billion years. Reaching Andromeda would take about 47 billion years, which is longer than the current age of the universe. New Horizons, the spacecraft that flew past Pluto in 2015, is travelling at about 36,000 miles per hour. Similar speeds, similar timescales, decades or centuries to reach the edge of our solar system, tens of thousands of years to reach neighbouring stars, billions of years to reach other galaxies. The Juno spacecraft, which studied Jupiter, reached speeds of about 165,000 miles per hour relative to Jupiter during its closest approaches. Still just a fraction of the Parker Solar Probe's speed, and still completely inadequate for interstellar or intergalactic travel. Here's the fundamental problem. All of these spacecraft are moving under conventional rocket propulsion, either chemical rockets or ion drives. And conventional rockets face a brutal limitation called the Tsiolkovsky rocket equation, named after the Russian scientist who first derived it in 1903. The rocket equation tells us the relationship between the change in velocity a rocket can achieve, the effective exhaust velocity of its engines, and the ratio of its initial mass to final mass. In simple terms, it tells us how much fuel we need to achieve a given speed, and the answer is almost always far more than you'd think. For example, say you want to accelerate a spacecraft to 10% of light speed, using a hypothetical nuclear fusion rocket with an exhaust velocity of about 10,000 kilometers per second. That's incredibly optimistic, way better than anything we currently have, but let's run with it. The rocket equation tells us that for every kilogram of payload you want to deliver at this speed, you need to start with about 22 kilograms of total spacecraft mass, meaning 21 kilograms as fuel. That might not sound too bad, until you remember you need to decelerate at the destination, which means you need to carry enough fuel to decelerate, which adds mass, which means you need more fuel to accelerate that mass, which adds more mass, in a vicious cycle. By the time you account for acceleration and deceleration, you're looking at much worse mass ratios. And that's just to reach 10% of light speed. Want to go faster? The fuel requirements increase exponentially. Want to reach 50% of light speed? Now you need thousands of kilograms of fuel for every kilogram of payload, even with these incredibly optimistic fusion rockets. And where are you getting this fuel? How are you storing it? How are you protecting it from the intense radiation of space? How are you dealing with the thermal management issues of running these fusion reactions for years or decades? These aren't just engineering challenges. These are problems that might be fundamentally unsolvable, given the constraints of physics and material science. But let's imagine we solve all of these problems. Let's imagine we develop perfect matter-antimatter annihilation engines, where we convert mass to energy with 100% efficiency, something that violates no laws of physics, but is currently completely beyond our capabilities. Even with this miracle engine, the energy requirements for relativistic interstellar travel are staggering. To accelerate 1 kilogram to 90% of light speed with perfect efficiency requires about 1.2 times 10 to the 17th joules of energy. To put that in perspective, that's roughly equivalent to the energy released by 30 megatons of TNT. That's 30 of the largest thermonuclear weapons ever built, just to accelerate 1 kilogram. A small spacecraft might mass 1,000 kilograms. A crewed spacecraft with life support, shielding, and all the necessary equipment might mass 100,000 kilograms. The energy requirements scale proportionally, and we're not even talking about intergalactic travel yet. We're still just talking about crossing the galaxy or reaching nearby stars. The energy requirements for intergalactic travel are orders of magnitude worse, because the distances are orders of magnitude greater, and you need proportionally more fuel to sustain the journey. The bottom line is this: our current spacecraft are laughably, pathetically slow compared to what we'd need for intergalactic travel. We're not within a few orders of magnitude. We're within 10 or more orders of magnitude. We're not in the same ballpark. We're not in the same sport. We're not even on the same planet. And this isn't just a matter of improving our technology. This is a matter of fundamental physics. The rocket equation doesn't care about your engineering ingenuity. The speed of light limit doesn't bend to your will. The energy requirements don't decrease because you want them to. We're trapped not by a lack of funding or a lack of will or a lack of clever ideas. We're trapped by the basic structure of the universe itself. And that brings us to perhaps the most crushing realization of all: the energy problem. The sheer, staggering, incomprehensible amount of energy required to accelerate even a small payload to the speeds necessary for intergalactic travel. Energy is everything. In physics, in engineering, in the real world, energy is the ultimate currency, is what allows you to do work, to change things, to move matter from one place to another, to accelerate spacecraft to high velocities. And when it comes to interstellar and especially intergalactic travel, the energy requirements are so vast, so utterly beyond anything we can currently produce, that they might as well be infinite. Let's start with the basics. How much energy does it take to move something? In classical physics, the kinetic energy of a moving object is 1/2 times mass times velocity squared. But that's only accurate at low speeds much smaller than the speed of light. As you approach relativistic velocities, you need to use the relativistic formula for kinetic energy, which accounts for the fact that the effective inertia of the object increases as its velocity increases. For a small object, say 1 kilogram, to reach 10% of light speed requires about 4.5 times 10 to the 14th joules of energy. That's 450 trillion joules, or about 125,000 kilowatt hours. The average American household uses about 11,000 kilowatt hours of electricity per year. So accelerating 1 kilogram to 10% light speed requires more than a decade of a household's energy consumption. For 1 kilogram, about 2 pounds, scale that up to a spacecraft. Even a small robotic probe might mass 100 kilograms. Now you need 45 quadrillion joules, or 12.5 million kilowatt hours. A typical large power plant might generate about 10 billion kilowatt hours per year, so you'd need the output of a large power plant for about 4.5 hours just to accelerate this small probe to 10% light speed. And 10% of light speed isn't fast enough for intergalactic travel. At that speed, reaching Andromeda would take 25 million years. You'd want to go much faster. Let's say 50% of light speed, which would cut the journey time to 5 million years. Still completely impractical for any crewed mission, or even most robotic missions, but let's see what it would take. At 50% of light speed, the relativistic effects become much more significant. The Lorentz factor, which describes how much time dilates and how much energy increases, is about 1.15 at 50% light speed. The kinetic energy of 1 kilogram at this speed is about 1.3 times 10 to the 16 joules. That's 13 quadrillion joules, or roughly 3.6 million kilowatt hours, for 1 kilogram. For a 100 kilogram probe, you'd need 1.3 quintillion joules. That's about 360 billion kilowatt hours, or roughly the total annual output of a large power plant. Just to accelerate. You haven't even dealt with deceleration yet, which doubles the energy requirement, and you haven't provided any power for the onboard systems during the multi-million year journey. Now let's scale up to something capable of carrying humans. A crewed spacecraft would need life support, radiation shielding, living space, food production capabilities, redundant systems, and a whole host of other equipment. You're easily looking at hundreds of tons, possibly thousands. Let's be conservative and say 100,000 kilograms or 100 metric tons. To accelerate this spacecraft to 50% light speed requires about 1.3 times 10 to the 21 joules. That's 1.3 sextillion joules, or roughly 360 trillion kilowatt hours. For perspective, total world electricity generation is about 25,000 terawatt hours per year, or 25 trillion kilowatt hours. So you'd need about 15 years of the world's total electricity production just to accelerate one crewed spacecraft to 50% light speed. And again, you need to decelerate, doubling this requirement. These numbers are so large they lose all meaning. They're abstractions. We can write them down, but we can't really grasp them. 30 years of the world's electricity production for one ship to make one journey. And we haven't even talked about where this energy comes from. Our current best energy sources are fossil fuels, nuclear fission, and renewables like solar and wind. None of these are remotely suitable for spacecraft propulsion at these scales. Chemical rockets, like those that took us to the moon, have exhaust velocities of a few kilometers per second. That's nowhere near fast enough. The fuel-to-payload ratio becomes absurd. You'd need thousands of tons of fuel to accelerate 1 ton of payload to even a tiny fraction of light speed. Nuclear fission is better. In a nuclear rocket, you heat propellant by passing it through a nuclear reactor core. This can achieve exhaust velocities of perhaps 10 to 20 kilometers per second, a significant improvement. But it's still not nearly enough, and you're carrying a massive heavy reactor that eats into your payload capacity. Nuclear fusion, where you fuse light elements like hydrogen into heavier elements like helium, releases much more energy per unit mass than fission. A fusion rocket could potentially achieve exhaust velocities of thousands of kilometers per second, which starts to get interesting. But we don't have working fusion reactors yet, not even stationary ones on Earth, let alone compact ones suitable for spacecraft. Matter-antimatter annihilation is the ultimate energy source. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to E-GeM-C2. This is the most efficient energy conversion possible in known physics. A matter-antimatter engine could theoretically achieve exhaust velocities approaching the speed of light. But antimatter is extraordinarily difficult to produce and store. We can create tiny amounts in particle accelerators, individual atoms or particles, but creating and storing kilograms or tons of the stuff is completely beyond our current capabilities. Antimatter annihilates instantly on contact with normal matter, so containment is a nightmare. You need magnetic or electric fields to keep it suspended, which requires power, which requires more mass, which compounds your fuel problem. And even if we solved all of these problems, even if we could efficiently produce and store antimatter and use it to power a spacecraft, the energy requirements for interstellar, let alone intergalactic travel remain staggering. We're talking about energy outputs that rival or exceed the total power consumption of entire civilizations. There's another aspect to this energy problem that's often overlooked. It's not just about having the energy. It's about converting that energy into thrust efficiently. Real rocket engines are not perfectly efficient. Some energy is wasted as heat. Some is lost to incomplete combustion, or imperfect magnetic confinement, or a dozen other inefficiencies. In practice, real engines might be 30% efficient, or 50%, or in the very best cases perhaps 70% or 80%. This means you need even more energy than the theoretical minimum just to account for losses. And then there's the problem of power generation over time. If your journey takes thousands or millions of years, you need power systems that can operate for those timescales. Solar panels? They degrade over time and become useless once you're far from any star. Radioisotope thermoelectric generators, like those used on Voyager? They decay with time. After a few decades, their power output drops below useful levels. Nuclear fission reactors. They need fuel, and they need maintenance, and they need to be shielded, and after decades or centuries, components will fail. You might think, okay, what if we don't carry the fuel with us? What if we collect it along the way? This is the idea behind the Bussard ramjet, a concept proposed in the 1960s. The idea is to use a giant magnetic scoop to collect the diffuse hydrogen that exists in interstellar space, fuse it for energy, and use the resulting thrust to continue accelerating. It's an elegant idea. But the problems are severe. First, interstellar space is really empty. The average density of hydrogen is about 1 atom per cubic centimetre. To collect enough to fuse, your scoop would need to be enormous, potentially thousands of kilometres across. The mass of the scoop and its magnetic field generators would be immense, eating into your acceleration capability. Second, at high speeds, the incoming hydrogen atoms hit your ship with enormous energy. They become a form of radiation, a deadly particle beam that would erode any material and irradiate anything aboard the ship. You'd need massive shielding, adding more mass. Third, the fusion reactions themselves are difficult to achieve and control. We don't have working fusion reactors on Earth yet. Building one that works inside a spacecraft using fuel collected from space and operating continuously for thousands or millions of years is probably impossible. The fundamental issue keeps coming back to the same point. The energy requirements are too high, not just slightly too high, not just beyond our current capabilities, but potentially beyond the capabilities of any civilization constrained by the laws of physics as we understand them. Some scientists have tried to calculate what level of technological development a civilization would need to achieve to carry out large-scale space travel. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, categorizes civilizations by their energy usage. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness all the energy of its star. A Type 3 civilization can harness all the energy of its galaxy. Humanity is currently at about 0.73 on this scale. We can harness a significant fraction of Earth's available energy, but not all of it. We're centuries, perhaps millennia, away from becoming a full Type 1 civilization, and we're unimaginably far from Type 2 or Type 3 status. Even a Type 2 civilization, with access to the full power output of a star like our Sun, about 4 times 10 to the 26 watts, would find intergalactic travel challenging. The energy required to send a single crewed spacecraft to Andromeda at relativistic speeds would represent a significant fraction of a star's total output for years or decades. And that's assuming perfect efficiency and perfect conversion of stellar energy into kinetic energy, which is impossible. The energy problem isn't just hard, it might be unsolvable. It might be a fundamental barrier that no amount of technological progress can overcome, because you can't extract more energy from a given amount of mass than EAMC2 allows. You can't accelerate matter to faster than light speed no matter how much energy you apply, and you can't make the distances any shorter than they are. We're bounded by physics itself. And this brings us to another uncomfortable truth about travelling at these speeds. Even if we could somehow solve the energy problem, the problem of time itself, and how it warps and bends at relativistic velocities. Time is not absolute. This is one of the most profound and disturbing insights of Einstein's theory of relativity. Time flows differently depending on how fast you're moving, and at the speeds necessary for intergalactic travel, these differences become enormous, creating a trap from which there might be no meaningful escape. Let's start with the basics of time dilation. According to special relativity, a clock that's moving relative to you runs slower than a clock that's stationary relative to you. This isn't an illusion or a trick. The moving clock genuinely experiences less time. If you synchronize 2 perfectly accurate atomic clocks, put one on a spaceship travelling at high speed, and then brought them back together, they would no longer be synchronized. The travelling clock would show less elapsed time. This effect is quantified by the Lorentz factor, usually denoted by the Greek letter gamma. The formula is gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low speeds, gamma is very close to 1, meaning time dilation is negligible. But as you approach light speed, gamma grows without bound, approaching infinity as you approach c. Let's put some numbers to this. At 10% of light speed, gamma is about 1.05. This means that for every 1,000 seconds that pass on Earth, only about 995 seconds pass on the spaceship. A small difference, but measurable. At 50% of light speed, gamma is about 1.15. For every 115 seconds on Earth, 100 seconds pass on the ship. More significant, but still not dramatic. But watch what happens as we keep accelerating. At 90% of light speed, gamma is about 2.29. For every 220 seconds on Earth, only 100 pass on the ship. Time is flowing more than twice as slowly for the travellers. At 99% of light speed, gamma is about 7.09. For every 709 seconds on Earth, 100 pass on the ship. Time is dilated by a factor of 7. At 99.9% of light speed, gamma is about 22.4. For every 2240 seconds on Earth, 100 pass on the ship. Time dilation by a factor of 22, and at 99.99% of light speed, gamma is about 70.7. Time flows more than 70 times slower for the travellers than for people on Earth. Now let's think about what this means for a journey to another galaxy. Andromeda is 2.5 million light-years away. If you could somehow travel at 99.99% of light speed, the journey would take about 2.5 million years from Earth perspective. But from your perspective aboard the ship, thanks to time dilation, the journey would take only about 35,000 years. 35,000 years might sound like a lot. It is a lot. It's about 7 times longer than human civilization has existed. But compared to 2.5 million years, it's almost nothing. This is often presented as the solution to the time problem. Sure, people say, the journey takes millions of years from Earth's perspective, but for the travellers it's much shorter. That makes it feasible. But does it really? Let's think this through. 35,000 years is still far, far longer than any human lifespan, even with radical life extension. It's longer than any human institution has existed. It's longer than recorded history. No spacecraft we can imagine would function for that long. No life support system would last. No materials would hold up to the constant barrage of cosmic radiation and micrometeorite impacts. You'd need either some form of suspended animation, which we have no idea how to achieve, or a generation ship where hundreds of generations of humans are born, live, and die aboard the spacecraft during the journey. And that brings its own impossible challenges. How do you maintain a stable, functioning society across hundreds of generations? How do you prevent genetic drift and inbreeding in a small population? How do you ensure the knowledge and skills necessary to complete the mission aren't lost? How do you keep people motivated for a goal that's centuries or millennia in their future? And that's assuming we're talking about a journey at 99.99% of light speed, which, as we've discussed, requires energy resources that we simply don't have and might never have. At more realistic speeds, say 10% of light speed, which is still wildly optimistic, time dilation is negligible. The journey to Andromeda would take 25 million years from both perspectives. There is no shortcut. There is no time dilation to save you. But let's say, for the sake of argument, that we solve all of these problems. We develop hibernation technology, or we build massive generation ships, or we upload our minds into computers that can last for tens of thousands of years. We somehow achieve 99.9% of light speed. We make the journey. What happens when you arrive? This is where the temporal disconnection becomes truly crushing. From Earth's perspective, you've been gone for 2.5 million years. Human civilization might not even exist anymore. Our species might have evolved into something unrecognizable, or gone extinct or transcended physical form entirely. The Earth itself will have changed dramatically. Continents will have shifted. Climate will have cycled through ice ages and warm periods. Species will have evolved and gone extinct. Everything you knew, everyone you knew, every institution and nation and culture, all gone, turned to dust, forgotten by history. You would return, if you returned at all, not as a hero but as a ghost, an anachronism, a living fossil from an ancient past. The languages you speak would be dead languages. The knowledge you carry would be archaic. The very reasons for your mission might be forgotten or irrelevant. This is the relativity trap. Time dilation means that while you can potentially survive the journey from your own perspective, you cannot survive it in any meaningful social or cultural sense. You become temporarily disconnected from your origin. You step out of history, and you can never step back in. And it gets worse, because we're not just talking about travelling to Andromeda. We're talking about escaping the Milky Way, and there are many galaxies in the universe, tens of billions within the observable universe. But the universe is not static, it's expanding, and that expansion changes everything. The expansion of the universe means that distant galaxies are receding from us. The farther away they are, the faster they recede. And at some distance, galaxies are receding faster than the speed of light. This doesn't violate relativity, because they're not moving through space faster than light. Space itself is expanding between us and them. This expansion creates what's called the cosmological event horizon. Galaxies beyond this horizon are causally disconnected from us. No signal from us can ever reach them, and no signal from them can ever reach us, because the space between us is expanding faster than light can cross it. As the universe continues to expand and this expansion continues to accelerate, driven by dark energy, this horizon gets closer. More and more galaxies slip beyond it, lost forever to the expanding space between us. If you wait too long to make your journey, your destination might literally become unreachable, not because you lack the technology, but because the universe itself has expanded beyond the point where that journey is possible. Right now, the cosmological event horizon is at a distance of about 16 billion light-years. Galaxies farther than this are already beyond reach, even with infinite technology and infinite time, and this horizon is shrinking. In the far future, if current cosmological models are correct, the only galaxies within reach will be those gravitationally bound to us, our local group. Everything else will have receded beyond the horizon, invisible and unreachable. This brings us to perhaps the most chilling aspect of intergalactic travel. It's not just that it's difficult, it's not just that it requires technology we don't have, it's that the universe itself is working against us, actively making the problem harder with every passing moment. The expansion of space is an adversary that cannot be fought, cannot be negotiated with, and cannot be overcome. The universe is not static. It's not a fixed stage on which galaxies sit motionless. It's dynamic, evolving, expanding. And this expansion is not just some abstract cosmological fact. It's a fundamental barrier to intergalactic travel that makes an already impossible problem genuinely, utterly unsolvable. Let's start with the basic fact. The universe is expanding. This was discovered in the 1920s by Edwin Hubble, who observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now called Hubble's law, tells us that the velocity at which a galaxy is receding from us is proportional to its distance. Now, it's important to understand what we mean by expansion. Galaxies aren't moving through space away from us, like cars driving on a highway. Space itself is expanding. Imagine an infinite rubber sheet with dots painted on it. If you stretch the sheet uniformly in all directions, the dots move apart from each other, but not because they're moving across the sheet. The sheet itself is getting bigger, carrying the dots with it. This is what's happening with space. The fabric of space-time itself is stretching. As it stretches, galaxies that aren't gravitationally bound to each other drift apart. The farther apart they are, the more space there is between them, and the faster they appear to separate. For nearby galaxies, this expansion is slow enough that gravity can overcome it. The Milky Way and Andromeda, for example, are actually moving toward each other, not away, because they're gravitationally bound. In fact, they're on a collision course and will merge in about 4 billion years, forming a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. Our local group of galaxies, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and about 50 smaller dwarf galaxies, is gravitationally bound. We're all orbiting around a common centre of mass. The expansion of the universe doesn't affect this group. We're held together by our mutual gravitational attraction. But beyond the local group, expansion dominates. Distant galaxies are receding from us at speeds that increase with distance. A galaxy 1 million light-years away might be receding at a few tens of kilometres per second. A galaxy 100 million light-years away might be receding at a few thousand kilometres per second. A galaxy 1 billion light-years away might be receding at tens of thousands of kilometres per second. And this is where things get truly bizarre. At a distance of about 14 billion light-years, galaxies are receding from us at the speed of light. And beyond that distance, they're receding faster than light. How is this possible? Doesn't relativity say nothing can move faster than light? It does. But these galaxies aren't moving through space faster than light. The space between us and them is expanding faster than light can cross it. This is a fundamentally different thing. Relativity limits motion through space. It doesn't limit the expansion of space itself. What this means is that there are galaxies we can see, galaxies that existed in the early universe whose light has taken billions of years to reach us, that we can never visit, even in principle, even with infinite technology, because they're now receding from us faster than light. The space between us and them is growing faster than we could ever cross it, even if we could travel at light speed. This defines something called the cosmological event horizon. It's the boundary beyond which events can never be observed by us, and which we can never reach, because the expansion of space prevents light or any signal from crossing that boundary. Right now, this horizon is at a distance of about 16 billion light-years, though the exact number depends on the specific cosmological parameters you use. But here's the truly disturbing part. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery. They found that the expansion of the universe isn't slowing down, as everyone expected. It's speeding up. The universe's expansion is accelerating. This was completely unexpected. Gravity is attractive. It should slow down the expansion, pulling galaxies back toward each other. But instead, something is pushing them apart harder and harder. Astronomers have named this mysterious force dark energy, though we have no idea what it actually is. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible substance that holds galaxies together through its gravitational effects, makes up about 27%. And ordinary matter, the stuff we're made of, the stuff stars and planets are made of, makes up only about 5%. The vast majority of the universe is stuff we don't understand. Dark energy has a peculiar property. Unlike matter or radiation, whose density decreases as the universe expands, dark energy's density appears to remain constant. As space expands, more dark energy appears, or more precisely, the total amount of dark energy increases because there's more space, and each unit of space has the same energy density. This constant energy density is what drives the accelerating expansion. What this means for intergalactic travel is devastating. The expansion of the universe isn't just a constant obstacle, it's a growing obstacle. It's getting worse over time. Galaxies that we could in principle reach today, if we had the technology, will become unreachable in the future. The cosmological event horizon is shrinking. We're racing against a clock, and we're losing. In fact, if the current cosmological models are correct, the ultimate fate of the universe is something called the Big Rip, or, more optimistically, heat death. In the heat-death scenario, the universe continues expanding forever, accelerating without bound. Eventually, the only galaxies within causal contact with us will be those gravitationally bound to us, our local group. Everything else will have receded beyond the cosmological event horizon, their light redshifted into undetectability, lost forever. Billions of years in the future, an astronomer in the Milky Way galaxy, the merger product of the Milky Way and Andromeda, would look out at the night sky and see almost nothing. No distant galaxies, no cosmic microwave background, red-shifted into oblivion. Just the stars of their own galaxy, and perhaps the remnants of our local group's smaller members, and otherwise darkness, eternal, expanding darkness. They would have no way to know that the universe was once full of billions of galaxies. They would have no way to deduce the Big Bang because the evidence would be gone, redshifted away, unreachable. They would think their galaxy was the entire universe, alone in an infinite void. This is our future, assuming dark energy continues to behave as it currently does, and it means that the window of opportunity for intergalactic exploration, already infinitesimally small, is closing. Not in our lifetimes, not in the lifetime of our civilization, but on cosmic timescales, it's closing fast. Now, there are some caveats. We don't actually know what dark energy is. Our models might be wrong. Dark energy might not be constant. It might strengthen or weaken over time. Recent observations from instruments like the Dark Energy Spectroscopic Instrument, or DESI, have hinted that dark energy might not be quite constant, that it might vary slightly over cosmic history. But even if this is true, it doesn't fundamentally change the picture. The universe is expanding, and that expansion makes intergalactic travel harder, not easier. There's another aspect to this that's worth mentioning. Even within our local group, even among galaxies that are gravitationally bound to us and not being carried away by cosmic expansion, the distances are enormous. Andromeda is 2.5 million light-years away. The Triangulum galaxy is about 2.7 million light-years away. These are our closest large galactic neighbours, and they're still impossibly far. And this brings us to a sobering realisation. When we talk about escaping the Milky Way, we're not talking about exploring the whole universe, or even a significant fraction of it. We're talking about, at best, reaching a few dozen nearby galaxies that happen to be part of our local group. That's it. That's the maximum extent of our possible reach, even in the most optimistic scenarios. Everything else, the tens of billions of galaxies in the observable universe, the vast cosmic web of galaxy clusters and superclusters, the strange and beautiful structures astronomers have discovered like the Great Attractor and the Sloan Great Wall, all of it is forever beyond our reach. Forever. Not just technologically difficult to reach. Fundamentally, physically impossible to reach. We are trapped in our local group, and even reaching the other members of our local group might be impossible. Which brings us to a closer examination of what this local group actually is, and what it means to be confined to it. Let's zoom out for a moment and look at the structure of our cosmic neighbourhood. Because when we talk about escaping the Milky Way, we need to understand where we'd be trying to go, and what the limitations are. The local group is the name astronomers give to the collection of galaxies that are gravitationally bound to each other in our immediate cosmic vicinity. It's not a precisely defined region. There's no sharp boundary, but generally we consider the local group to include all galaxies within a few million light-years that are moving together under their mutual gravitational influence, rather than being carried apart by cosmic expansion. The local group has two dominant members, the Milky Way and the Andromeda Galaxy, also known as M31. These are both large spiral galaxies, each containing hundreds of billions of stars. The Milky Way has a diameter of about 100,000 to 200,000 light-years, depending on how you measure it and what you include. Andromeda is slightly larger, perhaps 220,000 light-years across. There's a third large galaxy in the local group, the Triangulum Galaxy, or M33, which is about 60,000 light-years across. and contains roughly 40 billion stars. It's about 2.7 million light-years from Earth. It's unclear whether Triangulum is gravitationally bound to Andromeda, orbiting it as a satellite, or whether it's an independent member of the group that will eventually collide with the Milky Way-Andromeda merger. Beyond these three large spirals, the local group contains dozens of smaller galaxies, most of them dwarf galaxies. There are dwarf spheroidal galaxies, dwarf irregular galaxies, dwarf elliptical galaxies, each containing anywhere from a few million to a few billion stars. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the sky, are examples of dwarf irregular galaxies orbiting the Milky Way. In total, astronomers have identified somewhere between 50 and 80 galaxies in the local group, though the exact number keeps changing as we discover new faint dwarf galaxies. Most of these are satellites of either the Milky Way or Andromeda. The local group as a whole spans a region about 10 million light-years in diameter. Its total mass, including all the visible stars, gas, dust, and the dark matter that makes up most of the mass, is estimated at about 2 trillion solar masses. The centre of mass of the group lies somewhere between the Milky Way and Andromeda, probably a bit closer to Andromeda, since it might be slightly more massive. Now here's the key point. The local group is gravitationally bound. These galaxies are not receding from each other due to cosmic expansion. They're orbiting around their common centre of mass. In fact, the Milky Way and Andromeda are actually approaching each other at about 110 kilometers per second. They're on a collision course, and in about 4 to 5 billion years they'll merge. This gravitational binding means that the local group is, in a sense, isolated from the expansion of the universe. The space within the group isn't expanding. The galaxies aren't being carried apart. This is our island of stability in an expanding cosmos. But it's a small island. Andromeda, our closest large galactic neighbour, is 2.5 million light-years away. At the speed of light, which remember is the absolute cosmic speed limit that nothing with mass can reach, the journey would take 2.5 million years. At more realistic speeds, speeds that don't require impossible amounts of energy, the journey would take tens of millions or hundreds of millions of years. And that's just to reach our nearest large neighbour within our own gravitationally bound group. To reach a galaxy outside the local group, you'd need to overcome not just the distance, but also the expansion of space working against you. The nearest large galaxy cluster beyond the local group is the Virgo cluster, about 53 million light-years away. At light speed, 53 million years. At realistic speeds, billions of years. And the space between us and Virgo is expanding, making the journey longer the more you delay. So when we talk about escaping the Milky Way, in the most optimistic scenario where we somehow solve all the technical challenges, we're talking about reaching, at best, a few dozen neighbouring galaxies within our local group. That's the maximum extent of our potential civilization's reach. Not the universe. Not even a significant portion of our supercluster. Just our local group, and even that might be generous. Because there's another problem we haven't fully addressed. The sheer timescales involved mean that even if you could send a spacecraft to Andromeda, maintaining any kind of continuity or communication with that mission over millions of years is probably impossible. Think about it. You send a mission to Andromeda. It takes, say, 1 million years at some significant fraction of light speed. During that million years, human civilization on Earth will have changed beyond recognition. Nations will have risen and fallen. Languages will have evolved. Technologies will have advanced or regressed. Entire ages might come and go. The people who launched the mission will be dead for thousands of generations. The very reasons for the mission might be forgotten. And communication. Light takes 2.5 million years to travel from the Milky Way to Andromeda. Any message you send takes 2.5 million years to arrive. Any reply takes another 2.5 million years to get back. A single exchange of messages takes 5 million years. By the time you receive a reply to your first message, the civilization that sent it might not exist anymore. This isn't just a communication delay. This is a complete breakdown of causality over these timescales. You can't maintain a coherent civilization, a coherent culture, or even a coherent mission across timescales of millions of years. Everything drifts, everything fragments, everything becomes disconnected. So the local group isn't just a physical prison, it's also a temporal prison. Even if we could cross the distances, which we probably can't, we couldn't maintain the kind of continuity that would make the journey meaningful. And this brings us to the last refuge of the optimist, the last hope for those who refuse to accept these limits, the theoretical propulsion systems and exotic physics that science fiction loves and science largely dismisses. Warp drives, wormholes, quantum tunneling. Surely these offer a way out. Surely there's a loophole we haven't considered. Let's examine these ideas honestly and see if any of them offer genuine hope, or if they're just wishful thinking dressed up in equations. In science fiction, the heroes solve the problem of interstellar and intergalactic travel with ease. They have warp drives that bend space around them, allowing faster-than-light travel without actually moving faster than light locally. They have wormholes that connect distant points in space, creating shortcuts through the cosmos. They have quantum drives that somehow sidestep the normal rules of physics. The universe is theirs to explore. It's compelling, it's exciting, and it's almost certainly fantasy. Let's look at these ideas seriously and see what physics actually has to say about them. Let's start with warp drives. The concept comes from a 1994 paper by physicist Miguel Alcubierre. He proposed a theoretical solution to Einstein's field equations that involves contracting space in front of a spacecraft and expanding it behind. The spacecraft itself would sit in a bubble of flat space-time, surfing along on this wave of contracting and expanding space. From the perspective of the ship, it's not moving faster than light. From the perspective of someone watching from outside, it appears to cover vast distances in little time. It's a clever idea, and mathematically it works as a solution to Einstein's equations. But there are several enormous problems. First, the Alcubierre drive requires exotic matter with negative energy density, and not just a little bit. You need enormous amounts, quantities that might exceed the total mass energy of the observable universe, depending on the specific configuration. Negative energy density is not something we know how to create. Some quantum field theory effects, like the Casimir effect, produce what looks like negative energy in very specific circumstances, but these effects are incredibly weak and confined to microscopic scales. Scaling up the Casimir effect or similar quantum phenomena to produce the negative energy needed for a warp drive is completely beyond our current understanding. It might be fundamentally impossible. The energy conditions that prevent exotic matter from existing at large scales might be baked into the fabric of physics itself. Second, even if you could create the exotic matter needed, controlling it would be another challenge. You'd need to shape it into a very specific configuration around your spacecraft, maintain that configuration while you're moving, and somehow prevent it from interacting catastrophically with normal matter. Third, there's a causality problem. If you can use a warp drive to travel faster than light from one point to another, you can potentially create closed time-like curves, path through space-time that loop back on themselves. This is physicists speak for time travel, which introduces all sorts of paradoxes. Most physicists believe that the universe has some kind of chronology protection mechanism that prevents these paradoxes, though we don't know what that mechanism is. Fourth, even if all of these problems could be solved, there's a practical issue. How do you start and stop a warp bubble? If you're inside the bubble, you're causally disconnected from the outside universe. You can't steer. You can't accelerate or decelerate. You can't communicate with anything outside. You're trapped inside until the bubble collapses. And if the bubble collapses in the wrong place, you might find yourself inside a star or a planet. The bottom line is that warp drives, while mathematically permissible in general relativity, are almost certainly physically impossible. They require exotic matter we don't know how to create. They might violate fundamental principles of physics, and even if they could exist, they'd be incredibly dangerous and difficult to control. What about wormholes? These are hypothetical tunnels through space-time that connect two distant points. Travel through a wormhole and you emerge light years away, having crossed the distance in a short time. The math behind wormholes is solid. They're valid solutions to Einstein's field equations. But once again, there are enormous problems. First, wormholes, like warp drives, require exotic matter to keep them open. Without exotic matter with negative energy density, the wormhole collapses instantly. Anything trying to pass through would be crushed before it got halfway across. Second, even if you could keep a wormhole open, making it traversable, meaning something could actually pass through it without being destroyed, is another challenge. The tidal forces inside a wormhole might be enormous, stretching and compressing anything passing through. You'd need to carefully engineer the wormhole's geometry to make it safe. Third, there's the question of how you create a wormhole in the first place. It's not like there are natural wormholes just sitting around waiting to be used. You'd need to somehow manipulate space-time on enormous scales to create one. This would require energy and technological capabilities far beyond anything we can imagine. Fourth, even if you created a traversable wormhole, you'd need to move one of its mouths to your destination, but that mouth can't travel faster than light. So to create a wormhole connecting Earth to Andromeda, you'd first need to transport one mouth of the wormhole to Andromeda, which takes 2.5 million years at light speed. Once it's there, sure, you can use the wormhole for instant travel, but you still had to wait 2.5 million years to set it up. And finally, there's the same causality problem as with warp drives. Wormholes can create closed time-like curves, allowing time travel and all the paradoxes that entails. Most physicists believe this is physically forbidden somehow, though again, we don't know the mechanism. The reality is that wormholes, like warp drives, are fun to think about, and mathematically interesting, but almost certainly impossible in practice. They require physics we don't understand, exotic matter we can't create, and technology beyond anything we can imagine. They're not a solution to the problem of intergalactic travel. They're a fantasy. What about quantum tunneling? In quantum mechanics, particles can sometimes pass through barriers that classically they shouldn't be able to cross. This is called quantum tunneling. Could a spacecraft quantum tunnel across the galaxy? No. Quantum tunneling works for subatomic particles crossing barriers measured in nanometers or less. The probability of tunneling decreases exponentially with the width of the barrier and the mass of the particle. For a macroscopic object like a spacecraft to tunnel across light years of space is so improbable that the age of the universe isn't long enough for it to happen even once. The probability is effectively zero. What about other exotic ideas? Folding space, using higher dimensions, tapping into zero-point energy. None of these have any solid foundation in known physics. They're speculative ideas based on misunderstandings of quantum mechanics or general relativity, or they're simply made up for science fiction stories. The uncomfortable truth is that there is no loophole, there is no clever trick, there is no exotic physics that will save us from the fundamental limitations of space, time, and energy. The speed of light is absolute, distances are what they are, energy requirements are what they are, and the expansion of the universe is accelerating, making the problem worse, not better. We are bound by the laws of physics, and those laws are not negotiable. They're not subject to technological advancement. You can't engineer your way around EMC2. You can't invent your way past the speed of light. You can't clever your way through the expansion of space. This is the hardest lesson to accept. We want there to be a way. We want ingenuity and determination and human spirit to triumph over mere physical law. But they won't. They can't. The universe doesn't care about our dreams. It operates according to rules that we didn't make and can't change. So what does this mean for us? What does it mean for humanity's future? What does it mean for our place in the cosmos? We are alone. Not in the sense that we might be the only intelligent life in the universe, though that's possible, but in the sense that we are forever isolated from whatever other intelligent life might exist beyond our local group. We will never meet them, never exchange messages with them, never learn from them or share our knowledge with them. The distances are too great. The universe is too large. The expansion is too fast. This is a profoundly melancholy realization. It means that the vision of a vast galactic community of different civilizations meeting and trading and learning from each other is almost certainly fantasy. If there are other intelligences out there, and there almost certainly are given the sheer number of stars and planets, they're as isolated as we are, trapped in their own galaxies, confined to their own local neighborhoods, surrounded by an expanding ocean of space that they can never cross. It means that the universe is filled with intelligence, with consciousness, with beings looking up at the stars and wondering if they're alone, and yet all of these beings are forever separated by distances too vast to bridge. We're like lights on distant islands, visible to each other perhaps, but unable to communicate, unable to meet, doomed to flicker and die in isolation. But let's set aside the question of other life and focus on us, on humanity, on our future. What does this cosmic prison mean for our species? First, it means we need to be realistic about our prospects. We're not going to spread across the universe. We're not going to colonize thousands of galaxies. We're not going to build a cosmic empire spanning billions of light years. Those are fantasies, pleasant dreams that science fiction has sold us but that physics forbids. At best, we might spread across our own galaxy. The Milky Way is vast. It contains hundreds of billions of stars. If even a tiny fraction of those stars have habitable planets or moons, that's still millions or billions of potential homes for humanity. If we can solve the comparatively easier problem of interstellar travel within our galaxy, reaching stars tens or hundreds of light years away instead of millions, we could create a civilization spanning the Milky Way. This is not easy. It still requires technology far beyond what we currently have. It still requires overcoming immense challenges in propulsion, life support, radiation shielding, and long-duration spaceflight. But it's not impossible in the way that intergalactic travel is impossible. It's difficult, not forbidden. A galaxy-spanning civilization could be glorious. Imagine colonies on worlds orbiting other stars, habitats in the asteroid belts of distant solar systems, settlements in the clouds of gas giants or on the surfaces of frozen moons. Humans, or our descendants, adapted to 1,000 different environments, exploring and thriving in the vast realm of the Milky Way. This is our realistic future, if we have one at all. Not the universe, but our galaxy. Not unlimited expansion, but expansion bounded by physics and the light years that separate the stars. It's still an enormous playground. It's still more space than we could explore in millions of years, but it's bounded, finite, contained. And even this assumes we don't destroy ourselves first. Climate change, nuclear war, pandemics, artificial intelligence gone wrong, resource depletion, social collapse. There are so many ways we could fail as a species before we ever reach the stars. History is littered with civilizations that thought they would last forever and vanished within centuries. We have no guarantee of longevity. Second, this cosmic isolation means that Earth, and more broadly the Milky Way, are infinitely precious. This is all we have. This is all we will ever have. If we destroy our home planet, if we render it uninhabitable, there's no backup Earth waiting in another galaxy. There are potentially habitable exoplanets within our galaxy, but reaching them requires technology we don't yet possess, and they might not be suitable for human life without extensive terraforming. The Earth is irreplaceable. The Milky Way is irreplaceable. This needs to shape how we think about our future. We can't afford to be careless with our planetary home. We can't afford to treat it as disposable or as an experiment we can afford to get wrong. Because if we fail here, we fail permanently. Third, it means we need to adjust our cultural narratives. Science fiction has trained us to think of space as the final frontier, infinitely vast and infinitely explorable. And in one sense it is, but in another sense it's profoundly limited. We're not going to boldly go where no one has gone before across the entire universe. We're going to stay in our galaxy, if we're lucky, and even that will require more effort and ingenuity than most people realise. This doesn't make our potential future any less grand. A galaxy is plenty big enough for any civilization. But it does mean we need to let go of certain dreams. The dream of meeting alien civilizations from distant galaxies, the dream of cosmic-level empires, the dream of transcending our local region of space. These are beautiful dreams, but they're not realistic ones. Fourth, it emphasizes the importance of SETI, the search for extraterrestrial intelligence. If we can't travel to other galaxies to meet whatever civilizations might exist there, then our only hope of contact is through electromagnetic signals, radio waves, or laser communications travelling at the speed of light. These signals can cross the voids between stars much more easily than physical spacecraft can. If there are other technological civilizations in our galaxy, we might be able to detect their signals or send our own. The conversation would be slow. A message to a star 100 light-years away would take 100 years to arrive, and the reply would take another 100 years to get back. But it would be contact of a sort. It would confirm we're not alone in the cosmos, even if we can never physically meet. And if there are civilizations in nearby galaxies, in Andromeda or Triangulum, we might detect their signals even though we can never visit them. The conversation would take millions of years per exchange, but it would be possible in principle. It would be a beacon in the darkness, a confirmation that intelligence exists elsewhere, even if it's forever out of reach. Fifth, and perhaps most philosophically important, this cosmic isolation forces us to confront our own insignificance. We live on a tiny rock orbiting an ordinary star in a galaxy containing hundreds of billions of such stars, in a universe containing hundreds of billions of galaxies, and despite this vastness, despite the enormity of the cosmos, we are confined to one small corner of it. We will never see most of the universe. We will never explore it. We will never touch it. This could be crushing, or it could be liberating. It depends on your perspective. You could see it as a prison, a limitation, a cosmic unfairness, or you could see it as an invitation to appreciate what we have, to find meaning in our small, bounded existence, to recognize that grandeur is not measured by the distance we can travel, but by the depth of our experience, the richness of our culture, the beauty we can create and appreciate in our limited time and space. Humans have always been bounded. We're born, we live, we die. Most of us never travel more than a few hundred miles from our birthplace. Our lives are brief flickers in cosmic time. Yet we find meaning. We create art. We build civilizations. We love. We learn. We pass knowledge to the next generation. The fact that we're bounded by our galaxy instead of bounded by our planet doesn't fundamentally change this human condition. We're still finite beings in an infinite universe. We're still searching for meaning in a cosmos that doesn't provide it automatically. We're still alone with our thoughts, our cultures, our brief moment of awareness before the darkness. But here's the beautiful part. None of this diminishes our achievements. None of this makes our lives less valuable. None of this means our quest for knowledge and understanding is futile. We live in a vast, ancient, mysterious universe. We've learned an enormous amount about it through science. We've sent machines to other planets. We've looked deep into space and deep into time, seeing galaxies as they were billions of years ago. We've split the atom and sequenced the genome and landed on the moon. These are remarkable achievements for creatures whose ancestors were swinging through trees just a few million years ago. And we did them with our minds, with our curiosity, with our stubborn refusal to accept that anything is beyond our understanding. That's worth celebrating, even if the universe ultimately limits how far we can physically go. So here we are, back where we started, looking up at the stars, dreaming of other worlds, wondering what's out there beyond our little island of space. And the answer is almost certainly life, almost certainly intelligence, almost certainly civilizations as old or older than our own, perhaps wiser, perhaps more advanced, perhaps facing the same limitations we face. They're out there, somewhere, in the vast cosmic ocean, looking up at their own night skies, asking the same questions, reaching for the stars in their own way, but we'll never meet them. Not unless they're very close, within our own galaxy, and even then only if we can solve the tremendous challenges of interstellar travel. The ones in other galaxies, the vast majority of civilizations that might exist in the universe, they're forever beyond our reach, forever separated by distances so vast that the speed of light itself isn't fast enough to bridge them in any meaningful time frame. This is the truth we have to accept. We're trapped. Not by chains, not by walls, but by physics itself, by the structure of space-time, by the speed of a light, by the expansion of the universe, by the simple fact that the cosmos is too large and we are too small and too slow. The Milky Way is our home. It's our cage. It's all we'll ever have. And maybe, just maybe, that's enough. Because the Milky Way is beautiful. It's vast. It's filled with wonders we haven't yet seen, questions we haven't yet answered, discoveries waiting to be made. We have our work cut out for us just exploring our own galactic neighbourhood. We'll never run out of frontier. We'll never run out of mystery. So while we can't escape the Milky Way, while we're confined to this one spiral island in the cosmic ocean, we can at least make the most of it. We can explore every corner of our galaxy. We can send our telescopes ever deeper into space, looking back in time at the universe as it was. We can search for signals from other civilizations, hoping for contact even if physical meetings are impossible. We can appreciate the vast, ancient, beautiful universe we find ourselves in, even if most of it is forever out of reach. And most importantly, we can take care of our home, this Earth. This fragile blue-green marble orbiting an ordinary star is all we have right now. And it might be all we ever have if we can't figure out how to leave it and survive elsewhere. So we'd better treat it well. We'd better solve the problems we've created. Climate change, environmental degradation, nuclear proliferation, all the ways we're damaging our only home. Because there's no escape hatch. There's no backup planet waiting in another galaxy. There's just here. Just now, just us, and the choices we make, and the future we build or destroy with our own hands. So look up at the stars tonight, marvel at them, wonder about them. Let yourself dream for a moment about what might be out there, but then come back down to Earth. Because Earth is where we are, Earth is where we'll stay, and Earth is where we need to focus our energy and our love and our care. The universe is vast, we are small, but we are here. We are aware, and we are alive, and for now, that's enough. Before you go, if you enjoyed this exploration of cosmic limits and the physics of space travel, give this video a like. And if you want more deep dives into the mysteries of science and the universe, subscribe to the channel. I've got plenty more cosmic journeys planned, even if we're all stuck in this one galaxy together. Thanks for listening. Sleep well.